All right, good morning, everybody.
Good morning.
Good morning. I'm going to try to talk as loud as I can, but got vaccinated recently and it's been like, had a cold and now I kind of lost my voice. Anyway, it's been fun. Okay, so I don't think I'm actually sick, but. So we are going to talk today about, I don't know, try to set the stage a little bit for where some of the convection models that we're going to use, the correlations that we're going to use, come from. And I guess I want you to, we'll talk first about some of the experiments that we can do to actually measure convection as a value. But one of the things I want to hopefully get across today is a little bit of perspective on how you would build up correlations. Because I think there's, I don't know, certainly when I was sitting in your shoes, I had this idea that, okay, you've got correlations, you took data and you tried to fit all kinds of goofy equations to it until you found one that worked. Right? I know I had an internship where we were trying to measure something and we were trying to measure the tin content of an alloy. And we were using x-rays for that. And okay, so I took a lot of samples and then used our, measured it and then used our equipment and measured it and then fit like logs and exponentials and just threw kind of ugly equations at it until I got one that like you could squint and say, okay, that's kind of close maybe. So I think there's some, like that's how we kind of think of this as happening. But in reality, if you want to get good empirical models, you want to start from the physics. So we're going to look a little bit, for convection, we're going to have lots of kind of goofy looking empirical models. But the reason that the models look the way they do is not just completely random. It's based on the actual physics that's going on. So we're going to look a little bit, I'll try to gloss over as much as I can and go quick over it so we don't get totally lost in some of the math. But I want you to see before we like put up a whole bunch of convection models on the screen. I know all of you will be using empirical models at some point in your career to do something. Some of you will be responsible for building models, empirical models to be able to describe some physics. So I think having some perspective in this context, at least, some perspective on how we would go about actually doing that, I think is useful, even to be able to see it kind of in part, which is all that we'll really get the time to look at here. Okay, so before we do that, just a few notes. So we looked at similarity last time. This idea that if I have a system that is behaving one way, but maybe for some reason, maybe scale, maybe expense, maybe safety, I can't actually measure the real system. We can take aspects of the real system, design a similar system. And by similar, we mean more than just like you squint and it kind of looks the same. We mean they're physically similar. The physics that are happening in the two systems are the same. We can design a similar system and do experiments on that. So what would our experiments actually look like? Excuse me. So we'll look at, I'm super zoomed in. At measuring convection. Okay. So say I had some goofy shaped object. And I wanted to measure convection over that object. How would I actually do this? Well, you could put it in some flow, and you would fairly easily know, okay, what's the velocity of that? Say it's like air. What's the velocity of the air? What's the temperature? Easy things to measure. Then you would be able to figure out, you could figure out the size of the object, L. That would help you correlate measurements on this funny shaped object to another same geometry funny shaped object that maybe you're really interested in. Or perhaps it's this exact same one. Then we can calculate convection. We're trying aiming for a model of something like this. Q equals A H T S minus T infinity. So that's what we're aiming for. So it's really easy to measure T infinity. Area, if it's a goofy shaped thing, maybe that's a little bit harder, but we can at least estimate area. We're trying to measure then surface temperature and Q to find H. So this is going to be our unknown. We want to be able to measure all of the other terms. So how do we measure Q? Well, typically the easiest way is electrical heating. So we could set up maybe inside of the object. We have a voltage, which is driving a current through a resistor through the middle. I don't know why that line got. So there's a current going along through that wire. Maybe what we would really do is just say plant something in the middle of it. But then we can measure heat really easily because we know we can measure current really easily and we can measure voltage really easily. So we have some, like you can buy for a couple dollars little electrical heaters that you can hook up to a power supply, and you set the power on it. You set the voltage and measure the current on what that little electrical heater is. That's somewhere inside of your object. So this gives us I'm using E for potential because we have V's elsewhere. So E is, this is voltage. Okay, so we can really easily measure the power. Power equals current times voltage. That's the amount of power that's dissipated. That's turned from electrical energy into heat. So P equals Q. So the amount of heat that's being transferred from inside of the object out to the surroundings at steady state is going to be the power that's dissipated by your heater. This is the fluid temp, surface area, and this is just the surface temperature of your object. So if you use an electrical heater, it's actually really easily to directly measure heat, which means it's really easily to kind of back out an equation like this to find what the convection coefficient is. Right, in general, convection depends on a lot of things. Right, it would depend on the velocity, the size, the thermal conductivity of the fluid, the density of the fluid, the heat capacity of the fluid, the temperature of the surface, the temperature of the fluid, the viscosity of the fluid, and system geometry. So if you wanted to get a general description, you need to understand the effect of each of these. But we don't have to do an experiment where we vary heat capacity, and then an experiment where we vary viscosity, and then an experiment where we vary T infinity, and then a new experiment where we vary L. Like, we don't have to vary each of these variables independently to understand the whole thing. We have to be selective and only vary groups of variables that matter. Right, so the important we can vary groups of variables. Rho. So that's one group of variables. We don't have to vary each of those things independently. We vary like the whole business. And when we vary the entire Reynolds number, that captures all of the changes from those variables. No, not P. Same with the Prandtl number. The Prandtl number is nu over alpha, which is Cp mu over K. Okay, so we don't have to vary any of those separately. We can vary kind of them as groups, which is really nice because that makes we don't have to do, say, 5 experiments for velocity, and then 5 more experiments for length, and then do 5 velocity experiments at every different size. So there's 25 experiments. But then we have to do density too. So now we have to do 5 different densities at every different velocity and every different size. So there's 5 times 5 times 5, 125 experiments. And then we want to change viscosity. So we have to use 5 different viscosities at every one of those 125 experiments. So you very quickly, if you were trying to vary all of these parameters individually, you very quickly come to a place where you can't do enough experiments to understand the effect of all of these. But we can shrink it down to the most important groups of the important groups of parameters vary those, and then that will give us a description of all of the conditions that we could have seen. So practically, how would we do this? So Reynolds number equals rho u infinity mu, or rho infinity L over mu. So probably the most straightforward way to change Reynolds number is to change velocity. Another way to vary Reynolds number is to change the size of the object you're looking at. Maybe you're looking at like a little one and a big one. Density and viscosity, you can also change those. If you change to a different fluid, say you change from air to water, that's going to change the Reynolds number quite a bit because it's going to change the density and viscosity both. So another option is to change fluids. There are other ways too. If you change, for example, if you change temperatures, fluids will change viscosity and maybe density a little bit at different temperatures. That's kind of a less straightforward way. The easiest one is just changing velocity or changing size. So I would say that these three are the easiest, but there are other ways to change Reynolds number as well. You can see kind of what those are. So Prandtl is dp mu over k. So Prandtl, there are really two direct ways to change the Prandtl number. If you have a single fluid, if you change temperature, so change T infinity, the fluid temperature. This changes, at least for liquids, it doesn't work as well for gases, changes viscosity, like liquids thin out at higher temperatures, and they usually get thicker or more viscous at lower temperatures. Probably the most direct way to change Prandtl number, though, is just by changing fluids. Okay. So heat capacity, thermal conductivity, and viscosity are all very strong functions of like what your fluid is. So just changing fluids is kind of the most direct way to change what the Prandtl number is, although you can make some smaller changes by doing something like changing temperature. So, if you wanted to do, say, 4 different Prandtl numbers, you could probably do 2 different fluids, each at 2 temperatures, and kind of cover Prandtl number with that. You might not have to do 4 separate fluids. You could maybe do just 2. But there are other ways to kind of approach it too. But when we do, say, several different Reynolds numbers, several different Prandtl numbers, that gives us then a whole bunch of experimental data without a whole lot of experiments, which is kind of the goal, right? We don't want to take 10,000 experiments to be able to understand what's going on. We want to take like 8 and be able to understand what's going on. So that's the idea behind similarity. So we would find that relatively few experiments give lots of information. It gives information specifically on, it gives it on the convection coefficient, but more properly, it's going to give us information on the Nusselt number. So it's going to be, if we change, right, if we're using different fluids and different stuff, we're going to get different convection coefficients. But really, we're going to be looking at how the Nusselt number varies with Reynolds and Prandtl. Maybe how the average Nusselt number varies with Reynolds number and the Prandtl number. So we're not going to be looking just at the convection coefficient. We're going to be looking at the Nusselt number, which again will be able to kind of generalize things further than what we can with just the experimental data that we have. And that's kind of the strategy. If we can find the appropriate kind of chunks that are important, that helps us generalize our experiments without having to do all of the different possible permutations. So we can see, and I know I showed this just briefly last time. So this shows a little bit what that would look like. So you have, say on the x-axis, you have a couple different, so we did four different Reynolds numbers and 3 different Prandtl numbers. So a total of 12 experiments, not a whole lot. You think 4 different Reynolds numbers, that's like we had a flow and we could turn up to 4 velocities. So each one of those is maybe 3 different fluids and you do 4 velocities in each fluid. Not a huge set of experimental data. But because we put it in this framework, we can generalize that to different fluids, different sizes of objects, different velocities, different viscosities, different densities. Like we can generalize it so far beyond where we took our experimental data because we know how the physics is kind of behaving. So that allows us to take something like that, and what we see on the right side is we're taking kind of our experimental data and collapsing it down into a single correlation or a single model. Because we know how these different groups affect each other, or we know that these are the important parameters. What we're going to look at now is how would we figure out like what function the things should be, or kind of what it should look like how should the Reynolds number, the Prandtl number affect the, like how should the Reynolds number, the Prandtl number, and the Nusselt number be related to each other? So this gives us we don't know so we know that's true. But we don't know what that function should look like. We don't know kind of how we should build these correlations. So that's what we'll talk about briefly now. So kind of in general, what our approach is going to be. If I can jump ahead. So our general strategy for analyzing convection problems, step one, is we're going to use a mathematical model. So we typically are not going to be developing these. We're going to be finding them. Other people kind of did all the heavy lifting. We just have to find the right one and then be able to use it. If we can't find something that exactly fits the problem that we're trying to solve, then our job is to identify the key dimensionless groups. So again, if it's a problem that other people have solved, maybe we already know what those are. But if it's kind of a different problem, we might not know, like, what are the important physical mechanisms. So we'll learn fairly shortly, like if gravity plays an important role in the convection process. If we have like free convection happening on the wall, gravity matters, and then we have to take gravity into account. So that gives us a new dimensionless group called the Grascock number. But we have to figure out, like, what are the important forces and what are the important physical mechanisms in the specific problem that we have. There are different strategies to be able to do that. We're not going to cover them in detail in this class. We're mostly going to be looking at problems where we can pretty easily figure out what those would be. There's a process called the Buckingham pi theorem, which is kind of a generalized way to figure out what is the important physics that's going on. We're not going to actually do that, but that's a tool. If you come across like a problem that you're not sure what the important physics is, this is a way to kind of systematically figure out not only the important physics, but what are the important groups of parameters like Reynolds number and Nusselt number and Prandtl number. Where do all these things come from? How do we figure it out for a new problem that we're not exactly sure what's going on? This helps us identify experiments. If they're needed, if we need to do them, or we can help, use that as a tool to understand how somebody else's experiments are going to translate to our system. And then typically our last step is to modify of the model. So we kind of develop a mathematical model if we can, or get as close as we can. Then we look at doing experiments, and then we take our mathematical model and then we kind of adjust it and tweak it a little bit so it better fits the data. Okay. And we're usually doing something like what we saw just briefly before, where we're like looking at how dimensionless groups vary rather than how like an individual parameter is going to vary. Okay, so let's see this a little bit in action. And like I said, I'm going to skip over stuff. You're not going to be required to like go back and regurgitate this solution. But if we looked at flow over top of an object, right? If we want to look at flow around an object, we can start by looking at what happens for flow over a flat plate, and then use what we learned in that situation to kind of generalize up to, well, flow over a flat plate is different than, say, flow over a cylinder, like over a wire. But there should be like kind of similar physics going on. So we should be able to reach kind of similar models for the two. Like they're going to be relatively similar functions. For example, if we look at, okay, how is nu salt related to Reynolds or Prandtl number? If in a flat plate, it's like Reynolds number to the 1/2. In a flow over a cylinder, it's not going to be like the exponential of Reynolds number or the natural log or something. Like it's going to be maybe a power. So that's how we're going to kind of look at this. We'll look at a simplified system and then try to take that general description and extend it to other systems that don't really look like it, but are like close-ish. That kind of makes sense as a way to try to put as much of the physics of what's happening into our empirical model as we possibly can. That's how we get good empirical models. If they're like at least kind of sitting on top of a bedrock of actual physics of what's actually going on. So we choose flow over a flat plate because we can actually solve it. We're not going to solve it, but we'll look at what the solution is. The fun E. Okay, laminar flow over a flat plate. So we're going to simplify it quite a bit to be able to actually solve this. So we'll look at constant fluid properties. So things like density, thermal conductivity, viscosity, heat capacity. If we do this, then the then velocity is independent of temperature, which is nice because then we can kind of solve these as two separate problems. Okay, so then we solve first the fluids problem. To find what the velocity looks like. And then we can use that to solve the energy equation, the heat transfer problem. Okay, so again, I'm not going to show all the steps, but this is kind of our general strategy. We'll first solve the fluids problem, then the heat transfer problem. Okay, so here's our flat plate. Let's say it looks like this. We'll give it some real dimensions. So let's say it has length of 0.40 meters. This width is 0.20 meters. We know the surface temperature is 230 degrees. And we have air flowing over that top surface. So it's flowing at 25 meters per second and 25 Celsius. And it's at 1 atmosphere. Okay. We're going to assume like all the other surfaces, the sides, the bottom, everything is insulated. We're just looking at the top. Okay, so if we want to figure out what this is going to be, we first have to know what the properties are. So we're going to find the fluid properties at the average temperature. I chose those temperatures because it made my life easy looking up the properties, but that's the average temperature is 400 Kelvin. Then we can look up in table A.4. So T is 400 K. Rho is 0.8711 kilograms per meter cubed. CP 1.014 kilojoules per kilogram Kelvin. And then they always do something like this. They would write it like this. Mu times 10 to the 7 is 230.1 Newton second per meter squared. Just as a note, this is how our book writes it. This means mu is 230 times 10 to the negative 7. It means if we were to take the viscosity and multiply it by 10 to the 7, you'd get 230. There are different ways to write things for tables like this. This is how our book does in the property tables in the back. So just so you don't get confused on that. Then we would have kinematic viscosity is 26.41 times 10 to the negative 6 meters squared per second. Alpha 38.3 times 10 to the negative 6 meters squared per second. And Prandtl is 0.690. So those are kind of all of the different properties that we could want. What we're trying to do is, right, so we would solve this, find Q. Q is going to be equal to A H T infinity minus TS. Okay, so obviously this is going to be super easy to solve. We can find Q equals the area of the plate, 0.4 meters, 0.2 meters, times H bar, 25C minus 230C. So we just need H bar. What we're going to find is the properties themselves don't really matter. What we need is Reynolds number and Prandtl number to get the Nusselt number. So Reynolds number is mu infinity L over nu, which is 25 meters per second times 0.4 meters divided by 26.41 times 10 to the negative 6 meters squared per second. So you have to make sure that all of the units actually cancel out, which they do here. This is 3.8 times 10 to the 5. So the critical Reynolds number is about 5 times 10 to the 5. So the flow should stay laminar, although it's kind of going to be borderline at the end of the plate. So it's definitely going to be laminar over most of the plate. At the end, it maybe is borderline, but it probably should be laminar. Again, it's going to, the exact details are going to depend on like fluctuations in the free stream velocity. If your U infinity is not 25 exactly, if it's jumping around a little bit, then that's going to cause turbulence. But it should probably stay laminar. Okay, so if it remains laminar, then that allows us to actually do an analytical solution. So our first step is the fluids problem. Right, so we have for the fluids, our continuity equation is this. So this is conservation of mass. And the momentum equation is this. dy star 1 over the Reynolds number d squared u star d y star squared. So this is somewhat, both of these are kind of simplified down for this specific geometry. But you figured out what are the governing differential equations. Then you have to solve these with the appropriate boundary conditions. So our book does this in detail. I guess 7.2.1 is where our book goes through and actually like does the math and solves it. I encourage you just like flip to there at some point. Don't go through it yourself in detail, but at least like look through and go, okay, so this is kind of what they're trying to do. Basically, the solution is going to look a little bit like when we found the solution for a semi-infinite solid. Actually, it's going to be a lot of the same process, how you go about that. So you're going to get a similarity solution. Like a semi-infinite solid, we said that the temperature profile is going to be basically the same shape, and it's just kind of going to continue to grow. In this, we'll say the velocity profile is basically the same shape. It's just going to be kind of changing in that geometry, in that shape. It's going to be changing down the plate. So that allows us to find like a similarity variable. Which is u infinity over nu x to the 1/2. So again, y and x are not totally independent because they're kind of going to be coupled together as we go down the plate. So, right, what this tells us is so the velocity at the surface is always going to be 0. The velocity really far away is always going to be u infinity, and it's going to be kind of the same shape, although it's going to change in magnitude a little bit. Then we need, so that's going to be our independent variable, like the down the plate variable. Then we need a velocity-like variable. So this is our dependent variable. We define it as, we call it f, which is going to be a function of eta. And it's going to be, again, we're not doing this in detail, but it's going to be psi over u infinity nu x over u infinity to the 1/2. So actually the fluid stream function shows up. Again, I'm trying to save us from going through this in detail. But you transform your differential equation from velocity and position to these two other kinds of things. Right, so eta replaces x and y. F replaces velocity. So the reason we do that is because it gives us just, again, an easier way to actually get at the solution. We could do things like figuring out the shear stress, or figuring out what the velocity is at any given point. We could do that fairly easily from our solution. So we would now So the solution f is going to be some function of this thing eta. Again, not super important, but we could figure out what that function is. We could actually solve it. Okay, our step 2 would be solve the heat transfer problem. So the heat transfer problem would be U star dt star dx star plus v dt dy equals 1 over the Reynolds number times the Prandtl number d squared t star dx star, or sorry, dy star. Okay, and then we would have boundary conditions. The t star at 0 equals 0. T star at infinity is equal to 1. So the temperature at the surface is the surface temperature. The temperature far away is T infinity. So we would get kind of a similar approach. So we would use this same equation eta to capture the x and y part. So this is so now T star is some function of eta. Well, let me write it like this. Okay, so T star is going to be then not a function of x and y. It's going to be a function just of this similarity variable eta. This would give us, again, we saw a little bit about how you would actually do this in a previous thing. So I'm just kind of skipping over many of the details because it's not super important. But this would give us using eta transforms our PD into an ODE. And that specific equation would be d eta squared plus the Prandtl number over 2f dt star d eta equals 0. Right, so this is from the fluids problem. So we don't have a U component and a V component. We just have this single thing F. We don't have an X and a Y. We just have this single thing eta. But we could use that and solve this for basically any Prandtl number. So this the only thing that stays around really is the Prandtl number. So we could solve this numerically. to find T star anywhere. Okay, we're not going to do that, but let's say we wanted to find H, because that's like what we've been wanting to find. So if we wanted H, say at any point along the plate X, we know what H equals. H is going to be minus K fluid. Well, I guess let's write it this way. So let's not skip a step. So H at some given point along the plate is defined by like conduction through that first layer of fluid. Partial T, partial Y, evaluated at Y equals 0. So then we would transform this into kind of our new goofy looking variables. Using eta and T star. What this would give us is H X equals, so KF U infinity rho over mu X to the 1/2 d T star d eta evaluated at eta equals 0. Okay, so this would be our new equation, the same one up here, but transformed into these like goofy looking variables. Right, we would do that by saying, right, eta is a function of y, so we'd say y equals this big blob, and then we would throw that in wherever we see y. Same thing, we'd say T star equals this big funny looking, this group of variables, so we do some algebra, so we get a T equals, and then throw that in where at T. And out would pop this answer, which is the same equation, just switched into our new variables. This dt star d eta is just equal to a number. So this is equal to 0.332 times the Prandtl number to the 1/3. So again, we would have to dive into a lot more detail to show that better, but our book does in this section if you want to go through and if you care about where exactly this comes from. Then we could rewrite our H as 0.332. KF U infinity density over mu X to the 1/2 times the Prandtl number to the 1/3. Just for the sake of getting things to look nice. So we know Reynolds number is equal to U infinity rho. So the Reynolds number at this position, X over mu. And the Nusselt number at this position is equal to H times X over KF. So we'll do a little bit of massaging to be able to get these things to work out. So what we'll actually do is pull an X. We'll multiply both sides by X over X. to get that to work out. So we'll pull out this. So H equals 0.332 KF x to the minus 1. So we'll pull out an x to the minus 1. That will give us U infinity rho x over mu to the 1/2, Prandtl to the 1/3. And then we'll take these two and shift them over to the left-hand side. Okay, so this tells us that hx over times x over kf, which is equal to the Nusselt number at that position, 0.332, the Reynolds number to the 1/2, Prandtl to the 1/3. Okay. So we skipped a lot of parts, but we can figure out from the differential equations, we can solve this and actually solve it analytically and figure out how Nusselt number, Reynolds number, and Prandtl number go together. And then what we expect is other systems that are different than this should look basically the same kind of thing. So it should be like a power law thing where in general, we should see the Nusselt number is related to a constant, Reynolds number to some power, Prandtl number to some power. So that's kind of the general thing that we can take away. For flow, excuse me, Nusselt equals a constant, Reynolds number to a power, Prandtl number to a power. So C equals so C is a constant. In this case, it's 0.332. In another case, it's going to be something different. And then Reynolds number to the 1/2, Prandtl to the 1/3. They're going to be constants that are, maybe like an exponent that's less than 1 is kind of what we should expect. So this really gives us kind of a general picture of what we should probably be seeing. We're not quite there yet. So this is, if you want to go, this is the value at x. So that is the value at that location along the plate. We typically care about the average value over the whole plate. So if we want to find average value, right, the average convection coefficient is going to be 1 over the position times the integral from 0 to x of h dx. If we do that and plug in our relationship for h, So, right, what was, so if we plug in our HX value from above, I'm not going to do the math for it, but this tells us that HX bar is 2 HX. So our average new salt number that's the average H times X over KF, which is 0.664. Reynolds to the 1/2, Prandtl to the 1/3. Okay, and this is the equation that we typically will be using. So again, for our specific problem, which is right what we were trying to actually solve, right? What were we trying to solve? So we had flow over a flat plate. So let's figure out what is actually the average convection coefficient for this problem. So the Reynolds number was 3.8 times 10 to the 5. The Prandtl number was 0.690. So the new salt number, the average new salt number over the whole length L is equal to 0.664 times 3.8 times 10 to the 5 to the 1/2, 0.690 to the 1/3, which is equal to 350. Right, so once we actually get our model, using it is super straightforward. And that's one of the nice things, despite the fact that we built this on complicated physics and complicated math. Once we actually have it, it's really easy to use. We just plug in Reynolds number, we plug in Prandtl number, we calculate the new salt number, and then we know that the new salt number, right, that equals H bar. I'll use the subscript L just to say over that whole length L, times L over KF. That equals 350, which equals H bar times, so L was 0.40 meters, and the thermal conductivity of our fluid, 33.8 times 10 to the negative 3 watts per meter Kelvin. So H is 29.6 watts per meter squared Kelvin. So if we wanted to, we could plug this back into our model for heat transfer. Q equals A H bar TS minus T infinity. So this is 0.2 meters, 0.4 meters. H bar 29.6. And this is 230 minus 25. So Q is 485 watts. Okay. So we use it, once we get it, we use it just like we've always used it. The reason I went through, even like as hand wavy as we did, went through the math is because I think otherwise, if you said, oh, the new salt number is related to Reynolds and Prandtl, you go, okay, maybe that's fine. But like, why Reynolds number to the 1/2 and why Prandtl to the 1/3 power? Like, you just get weird powers and you get this weird constant 0.332. Like, what's magical about that? Well, those are all things that actually drop out of an analytical solution for that problem. And when we build other models, we're going to have like weird coefficients and weird exponents. And that's because we're going to take data, kind of like what we did, what this is showing here. We're going to take data that we have and fit it to our general equation. Oh, I hate when it does this. It like all of a sudden stops. Okay, I'm not writing there. So the new salt equals C Reynolds to the M, Prandtl to the N. So we're saying that has to be our basic model, and we're looking for some model like that. So that's what we're taking our data there on the left-hand side and collapsing it so that it looks like some version of that function. And that function isn't like random. We didn't just make it up. We have it, we say it's similar to what the physics should be in a flat plate. And that's really, I think, an interesting thing, a different way of thinking maybe about how you build up like weird empirical models like this, is you can actually build them up and get at least an idea of how these things should be related if you can start at the fundamental physics of what's going on, even if it's like a much simpler problem. We'll use a model like this to look at, flow over cylinders or over wires or, all kinds of different things. But to look at turbulent flow, we'll say all of those should be like ballpark similar. So I don't think we have time to really dive into to much beyond this. So I think we'll just stop there. And we'll dive in a little bit more to some of this on next time. So thanks for sticking around and following along to probably too much math. But I hope you guys have a good rest of the week. We'll see you back on Thursday.